Hello everyone, I welcome you to my class. Today we'll read lecture 2 on 3 dimension, and today we are going to learn the equation of line in space. We know that equation of a line in space can be uniquely determined, provided the line passes through a point and has a fixed direction. So based on that concept, that we are going to discuss the first case, that when you can find an equation of a line, and in space, that is the equation of a line through a given point and parallel to a given vector b. So we are going to discuss that particular point, that here a line L is given, that line L passes through a fixed point A, and this line is parallel to vector b. So we are going to find the equation of this line. Now, let us assume that the position vector of A, since it's a known point, let the position vector of A with respect to OS A, and will be assuming one arbitrary point on the line, say P be an arbitrary point, and position vector of P be R. Now, this line is parallel to B. So let us start how we can just derive the equation of the line. Let the position vector of A be A, and position vector of P, which is arbitrarily chosen, that is P. Let the position vector of P be R. Let the line parallel to vector B. Now, since the line L is parallel to B, then how can we relate the vector AP with B? We know that AP and B are parallel. This AP and B are parallel vectors. So how do you write two parallel vectors? How do you connect two parallel vectors? We know that if AP and B are parallel vectors, then one vector can be written as a scalar multiple of the other vector. So you can just write the expressions like that. Since AP and B are parallel. Since AP and B are parallel, therefore we can write AP lambda B, where lambda is any real number. Now let us try to find out what is AP from the figure. So just draw the figure here. And let us assume that is a line, and we have taken the point, fixed point as A, and arbitrarily chosen point is P. This is A, and position vector of A we have taken as A, and this is R. And we have taken that the parallel vector is B, vector B. This is AP, this is OP, and this is the origin, and this is X, Y, Z. So it will be easy for us in case if I just draw it once more. In fact, you need to draw only once, right? Now AP, you're just going to find AP from this triangle, that is OAP. So if we use the triangle law of vector addition on OAP, triangle OAP, we can just write OA plus AP is equal to OP. So this gives us the value of AP. So AP can be written as, and AP, we can write AP as OP, factor OP minus OA. So we just replace this, that is AP is equal to OP minus OA, right, equal to lambda B. So what is OP? OP is vector R, this is A equal to lambda B. Fine. So we got an important equations. Now, for any value of lambda, so it will give a point, right, any arbitrary point on this line. So therefore, the equation of the line can be taken as R, we can just write in a standard form A plus lambda B. So this is the vector equation of the line L. Now let us discuss the Cartesian form. How can you just convert the Cartesian form from the vector form of equation of line? So we'll just start Cartesian form of equation of the line. So we'll just discuss about that. Cartesian form of equation of the line. Okay. We know that when we are just going to write the Cartesian form, so we need to know the coordinates of the points. Let the coordinates of the fixed point, that is what is point is given, let the coordinates of A, B, x1, y1, z1 and coordinates of P, B, that is the arbitrary point B. Generally the arbitrary point coordinate we just take as x, y, z. Let the coordinates of A, B, x1, y1, z1 and the coordinates of P, B, x, y, z. Okay. Also we should know the direction ratio of the line. Also you can just let us assume that direction ratios of the line B. Let us assume that the direction ratios of the line B A, B, C. Right? So we have assumed the coordinates of A as x1, y1, z1 and the coordinates of P, that is arbitrary point, as x, y, z, and we are also assuming that let the direction ratios of the line be A, B, C. So we'll just write here what is the equation of the vector equation of the line, standard form. This is the vector equation of the line that we have just derived. Now we'll just write R in terms of x, y, z. So now in place of R, we can just write, we know that a vector can be written in terms of the component form, that is xi cap y, j cap and z k cap, right? So A also similarly can be written in terms of, because A is a position vector of A and we have assumed that the coordinates of the fixed point A as in terms of x1, y1, z1. So therefore A can be written as x1 I cap, y1 j cap and z1 k cap. Then this is A plus lambda and this is vector B. So vector B, which is parallel to the line, and we know the direction ratio of the line, so therefore B can be, the vector B can be written in terms of the direction ratio, that is A I cap, B j cap and C k cap. So you can just simplify like that, you just transpose these terms, right? So x I cap minus x1 I cap. In fact, we can just take I cap common, like x minus x1 I cap plus. So similarly, we bring this, we will transpose all the three terms, right? That is y minus y1. We'll take j cap common, and similarly, we'll get a third term, j minus j1 k cap, and right hand side it will be lambda a I cap plus b j cap plus c k cap. Now let us compare the coefficient of I, j and k from both the sides. So comparing the coefficients, comparing the coefficients of I, j and k. If we compare the coefficients, okay, ijk, we get, if we compare the coefficient of I, we get x minus x1 is equal to, what is the coefficient of I cube in the right hand side? It's lambda A. So if we just simplify this, so if we write this expression in terms of lambda, so it would give us x minus x1 upon A equal to lambda. So let us note down this. Yes, this gives us x minus x1 by A equal to lambda. Similarly, when you will be comparing the coefficient of J and coefficient of K, we will be getting similar terms. So you can just write similarly. Similarly, what you will get? Y minus y1 by B equal to lambda, and Z minus z1 by C equal to lambda. Now we can eliminate lambda from the three expressions. Therefore, eliminating lambda, we get x minus x1 by A, y minus y1 by B, and z minus z1 by C. So which is the Cartesian form of the equation of the line L, right? And in case we know the direction cosine, instead of the direction ratio, you want to write the equation in terms of the direction cosines, and we can just write the equation of the straight line in terms of Ln. So x minus x1, y minus y1 by m, and z minus z1 by n. So this is the equation in terms of the direction cosines, where Ln and n are the direction cosine of the given line. Okay, so we have discussed this 2 points, that when an equation of a line, we need to find out where the line passes through a fixed point and the line is parallel to a vector B. So we have seen that the equation of both the vector as well as the Cartesian forms are very simple. Okay, so yes, so this is the vector equation of the line, that is R equal to A plus lambda B, and this is a very important equations. So derivations as well as every point related to this is very important, but many of the questions are solved using this particular equation of the line. So similarly, we have also discussed about we have also formed, right? We have also derived the Cartesian form of equation of the line, right? It is x minus x1 by A, y minus y1 by B equal to z minus z1 by C. What is x1, y1, z1? This x1, y1, z1 are the coordinates of the given point. Remember this. And A, B, C are the direction ratio of the line. Okay. Now, we can just move to the next concept, that we'll discuss this important point, that is a second point of discussions today, that equation of a line passing through two given points. Okay, we know that equation of a line can be uniquely determined by this case also. So we know that through two given points, one and only one line can pass through. So we are going to discuss that particular point. Say from the diagram, we can definitely understand that the moment we use ABC, these are generally assumed to be the given fixed point. Here AB, that means this line passes through AB, right? These are a fixed point AB. And P is any arbitrary point on the line. And also we are assuming, like A, small a, be the position vector of A, and this B vector be the position vector of B, and we take R as a position vector of the arbitrarily chosen point P. So let us note these points. Let A be the position vector of the point. Let A be the position vector of the given point of the given point A. So just assume the coordinates of A, that is x1, y1, z1, and B be the position vector of the other point B. Okay, we'll assume the coordinate of B as x2, y2, z2. Okay, we'll assume the coordinate, the position vector of A and B. Now, let us consider R be the position vector. So let's move to the next page. R be the position vector of the arbitrary let R be the position vector. Let R be the position vector of the arbitrary point P. So let's take the coordinate of P as x, y, z. So to derive the equation of the line, so I should again draw this because I need the figure to explain. So I'll just redraw the diagram here. Okay. This will take this is okay. We'll just take this one as we'll use another color. Okay. Right. This is one. Right. So this is a point A, and say this is point P, and this is point B. Fine. We have taken this is A, this is B, and this is R, and this is a line. Okay. Now, the point P, right? Which position vector is R? Most important point. Point P will be lying on AB, right? That means APB will be collinear if AP, that is vector AP, is collinear with vector AB. That is, if you can just write the point P, the point P will be, the point P will lie on the line. Okay, if and only if the point P will lie on the line, if and only if AP, vector AP will be collinear with AB. In case AP and AB, right, these two vectors are collinear, so you can just write one vector in terms of the other vector. So you can just write AP is equal to lambda AB. So you can just write the point P will lie on the line if and only if AP is collinear with AB, or we can just directly write AP lambda AB. Fine. So, which is very important. Now, we just write the value of AP, this, okay, for that, so this is O, this is X, this is Y, this is Z, right? For that, we are going to use the triangle of addition from OAP. So we need to find AP. So we know that AP is equal to OP minus OA. Just now we have discussed about that. So we need AP. So AP can be written as OP vector OP minus, because OA plus AP gives us OP. OA plus AP is equal to OP. Therefore, AP will be OP minus OA. OA. Fine. Equal to lambda. So lambda is any real number AB. Now AB, how to find AB? So to find AB, we'll be using the triangle of vector addition on OAB. OAB. And that means OA plus AB, right? OA plus AB gives us what? OB. So from there you can find out OB. AB is equal to OB minus OA. Right? OB minus OA. So this implies, what is OP? OP is vector R minus A equal to lambda. Find OB. OB is equal to vector B minus A. Right? So R minus A equal to lambda, B minus A. So we can just go to the next steps. Therefore, R equal to A plus lambda B minus A. So which is the vector equation of the line, which is also a very important equation of line, and this is a line when a line passes through two given points. Here A and B, right? These A and B are the direction, A and B are the position vector of the given points. Okay, so we just now find, okay, let us, yes, from this particular equations, again from this particular line, right, we got the equations in the form of this r equal to A plus lambda B minus A. Now let us again derive the Cartesian form of equation of this line L, right? For that, so we should know the coordinates of A, P, B, which I already have mentioned that, so I hope we have mentioned about that, the coordinates, already have taken the coordinates, right, yes. What? That coordinates of A we have taken as x1, y1, z1, okay. We have taken the coordinates of A as x1, y1, z1, coordinates of B as x2, y2, z2, and coordinates of P, okay, which is an arbitrarily chosen point. We always take the coordinates as x, y, z. So based on that, yes, it's going to derive, yeah, the Cartesian form. So let us derive that. Okay. Cartesian form of equation of the line. So as in the previous theory also, we have derived the Cartesian form from the given equation. So directly we can just start deriving from these equations. So r is the position vector of the arbitrarily chosen point, and the coordinates of P is x, y, z. So r can be written as x I cap, y j cap, and z k cap. Fine, r I have written. Then similarly A also I write in the component form. A is the position vector of A. The coordinates of, we should know the coordinate of A as x1, y1, z1. So A can be written as x1 I cap, y1 j cap, and z1 k cap. Now lambda B. P is the position vector of this B. Small b is the position vector of the second point B, and whose coordinate is x2, y2, z2. So therefore B can be written as x2 I cap, y2 j cap, and z2 k cap. Fine. Okay. Yes. Minus. So A can be written as x1 I cap, y1 j cap, z1 k cap. Fine. Okay. Now similarly, what I'm going to do is, the way we have derived the previous Cartesian form, here also will be comparing the coefficient of ijk. For that, what I'm going to do is, I'll just transpose these terms, right, to the left hand side. So if I transpose, what I'm going to do is, I'll take I cap and j cap, k cap common. So I'll get x minus x1 I cap. Then similarly, I'll get y. If I transpose this term there, so I y minus y1 j cap and j minus j1 k cap. This equal to. So from there also, what I am going to do is, I'll be taking this one, that I cap common, right, from there. Okay, so if I take I cap common, what I am going to write is, so you can take lambda common. So if I take I cap common, I am going to get x2 minus x1 I cap. So I can just take lambda common. So I'll get, first term will be x2 minus x1 I cap. Similarly, what I will get, y2 minus y1 j cap plus, and z2 minus z1 k cap. So if I compare both sides, right, if I compare, what I am going to get, I can write here now, okay, if I compare the coefficient of I in the left hand side and the coefficient of I in the right hand side, so what will be the first time? So comparing the coefficients, comparing the coefficients. So I just get the first term as x minus x1, right? X minus x1 is equal to, what is the coefficient of I in the right hand side? It's lambda x2 minus x1. Done. So therefore, it is just right in terms of lambda. These expressions can be written as x minus x1 upon x2 minus x1 equal to lambda. Just similarly, we can write the second and the third term. Second and the third term will be y minus y1 by y2 minus y1, right? Should be y2 minus y1 equal to lambda. And what will be the third term? Okay, the third term will be, so you can just write the third term, and z minus z1 by z2 minus z1 equal to lambda. So we got the three expressions in terms of the lambda. And finally, we are going to write the Cartesian form of the line. So what I am going to do is, okay, we are going to eliminate lambda from the three expressions. Therefore, we can just write x minus x1 by x2 minus x1 equal to y minus y1 and y2 minus y1 and z minus z1 by z2 minus, okay, z2 minus z1 done. So which is the equation of the line, right? Passes through two given points. What is x1, y1, z1? x1, y1, z1 are the coordinates of one point, one given point. x2, y2, z2 are the coordinates of the other given point. So which is also a very, very important equation of line. Okay, in this today's video, okay, in lecture 2, we have discussed about the two-vector equation of lines and two Cartesian form. Okay, for case 1 and case 2 on two different cases that we have discussed today. Okay, in the next video, like we are going to discuss about some very important point like distance between lines and angle between line. All these points we are going to discuss in the next video. And thank you so much for watching my video. And in case if you have not subscribed my channel, please do subscribe. And thank you so much.